Good afternoon, my dear students. We're still in chapter 1. Let's start with lesson 3, quantum numbers. In the previous session, we have discussed that Schrödinger applied the ideas of Planck, Einstein, de Broglie, and Heisenberg and established something which is called wave mechanical theory of the atom. He managed to derive a wave equation. After solving this equation, we are gonna introduce 4 numbers which are called quantum numbers. To determine the energy level of an electron in multi-electron atoms, we should know the 4 quantum numbers. So we have to solve first Schrödinger's equation to get the 4 quantum numbers which describe the place which is high probable to find an electron. These 4 quantum numbers are. To understand the idea of quantum numbers, let's think what do you need to know or to find out where you live. First, you have to know your state or your country. Second, you have to know the city you live in. Third, you have to know the street. And finally, you can reach your home. By solving Schrödinger's equation, you can find the place of high probability to find an electron, which is called orbital. But first, you have to get the 4 quantum numbers. The first one is called the principal quantum number. The second one is called subsidiary quantum number. The third one is called magnetic quantum number. And the last one is spin quantum number. Let's discuss the 4 of them in details. Principal quantum number. This quantum number used to define the following: the order of principal energy level and the number of energy levels for the heaviest atom, the atom which contains the largest number of electrons, is 7 energy levels. Number of electrons required to fill a given energy level from the relation 2n to the power 2, where n is the number of energy levels and the principal quantum number or the number of energy levels are integer numbers from 1 till 7. We can here remember the rule from model 1 of electronic configuration. The first energy level, which is k, its number is 1. So 2 times 1 to the power 2, we apply the rule 2n squared. So it will filled with 2 electrons. The second energy level completely filled with 8 electrons. The third energy level is filled with 18 electrons, and n is filled with 32 electrons. And don't forget that this rule is applied only till the 4th energy level, not for the 5th, 6th, or the 7th. Because if this rule is applied for upper energy levels, the atom will be unstable. The principal quantum number has a positive integer numerical values from 1 to 7, as we mentioned in the previous slide. Each value is expressed by an alphabetical letter. So energy level 1, K, energy level 2, denoted by L, energy level 3, M, N, O, P, Q, till we reach the 7th energy level, which is called Q. So don't forget to mention that as we move away from the nucleus, or as the radius of the energy level increase, the energy of it will increase. So we have to know that K has the lowest energy and Q has the highest energy. The quantum number is subsidiary quantum number. This number determines that each energy level is divided into something called energy sublevels. And these sublevels equal the number or the principal quantum number, which means that the energy level that its quantum number is 1 contains 1 sublevel, and the second one, its principal quantum number is 2, is divided into 2 sublevels, and the third energy level composed of 3 sublevels, and the 4th energy level composed of 4 sublevels. So the subsidiary quantum number determines that each energy level divided into energy sublevels. The energy sublevels are denoted by symbols and numbers. Let's start with the symbols. Energy level 1, which is K, has only one sublevel. Its symbol is S. Energy level L has two sublevels, which are S and P. Energy level 3 consists of three sublevels, which are S, P, and D. The fourth energy level consists of four sublevels, which are S, P, D, and F. Let's know how to determine the subsidiary quantum number of these four sublevels. We have to calculate a range for each energy level to know the subsidiary quantum number for each sublevel. The range is from 0 to n minus 1, and of course n is the number of energy level. In the following slide, we are going to calculate the subsidiary quantum numbers for each sublevel. Let's start for energy level K. K, its principal quantum number is 1. So apply the range from 0 to n minus 1. From 0, remove the n and put the number of energy level, which is 1. From 0 to 1 minus 1, which is 0. So we have K consists of one sublevel called S, and its subsidiary quantum number is 0. Let's take another example. For energy level L, its number is 2. So apply the range from 0 to n minus 1. 0, remove n and put 2. 2 minus 1, which is 1. So we have here the range from 0 to 1. We can notice that L divided into two sublevels. The first one is S. Its subsidiary quantum number is 0. The second sublevel is P, and its subsidiary quantum number is 1. By applying this range to the third and the fourth energy level, we can get these values. So we have S, its number is 0. P, its number is 1. D sublevel takes 2, and F takes 3. You have to know that there is a small difference in the energy of energy sublevels in each energy level. They can be arranged according to increasing in their energy in the following order. S has the lowest energy, P has higher energy than D sublevel, and the highest one in energy is F sublevel. As you observe here, in the second energy level, for example, we have 2S and 2P. Which one has lower energy? Of course, 2S. You can observe here in the third energy level, we have 3S, 3P, and 3D. Okay, you can observe here that 3S has the lowest energy. Then we have 3P higher, and the highest one here is 3D. And you can apply this for all the energy levels. Let's take an example. What are the probable subsidiary quantum number values when n equal 4? Of course, we have known that the principal energy level consists of number of sublevels which are equal to its numerical value. That means energy level 4 will have only 4 sublevels, which are the range between 0 to n minus 1. So you have to apply the rule. From 0 to 4 minus 1. So we have the range from 0 to 3. They are sublevel 0, which is S, P, D, and F. Let's move to the third quantum number, which is magnetic quantum number, and it is denoted by ML. This quantum number determines the orbitals within a certain energy sublevel. We have here a new thing. Each energy level, as we mentioned before, divided into energy sublevels. Each energy sublevel divided into a number of orbitals. So magnetic quantum number determine the number of orbitals within a certain energy level. How can we determine the number of orbitals in each energy level? From the relation 2L plus 1. And L is the subsidiary quantum number. It also determines the orientation of orbitals. The word orientation means their motion in space or their shape in space. So the magnetic quantum number tells us two things. Number one, the number of orbitals from the relation 2L plus 1. The second thing is the orientation of orbitals or the shape of orbitals in space. It is represented by odd integer number ranging from negative L to positive L. And as we mentioned before, L is the subsidiary quantum number. So the magnetic quantum numbers take range from negative L to positive L. To know how many orbitals in each sublevel, let's try to apply the relations from the previous slide. Apply the relation 2L plus 1 to know the number of orbitals. For sublevel S, L equals 0. As we mentioned before, S has a subsidiary quantum number equals 0. Apply the relation 2 times 0 plus 1, which is equal 0. So we have in S sublevel only one orbital and its magnetic quantum number is 0. Let's try again. Let's try with the second energy level. Apply the relation 2L plus 1 for P sublevel. As we mentioned before, B sublevel, its subsidiary quantum number equal 1. So 2 times 1 plus 1, we will have here 3 orbitals. So P sublevel divided into 3 orbitals. How about their magnetic quantum numbers? From negative L, L here is 1. So the ranges or the value of magnetic quantum numbers for P sublevel, negative 1, 0, and positive 1. And by applying this rule for the third and the fourth energy level, we can get that D sublevel consists of 5 orbitals. Their magnetic quantum number ranges from negative 2 to positive 2. The fourth sublevel F, composed of 7 orbitals, magnetic quantum numbers range from negative 3 till positive 3. The following table shows the relation between subsidiary quantum number values and the probable values of magnetic quantum number for the 4 energy levels. We have to know that the orbitals of the same sublevels are equal in energy but differ in the direction and the shape in the space. So the orbitals of P sublevel, for example, are equal in energy but their direction or their orientation in the space vary. Let's start with the shape of the first sublevel, which is S sublevel. S consists of one orbital and its shape is a spherical shape around the nucleus. As you observe here, we have one S orbital and here is 2S orbital which is a little bit bigger than 1S, but both of them has spherical symmetrical shape around the nucleus. Let's move to P orbitals. P sublevel consists of 3 orbitals. Their shape like 2 pairs meeting head to head or dumbbell shaped. In the following slide we can show the shape of P orbitals. As you observe here, we have 3 orbitals. One called px orbital, it's on the x-axis, and the second one py orbital, and the third one pz orbital. their shape, like this one, they are all of them perpendicular to each other in the form of dumbbell shape or two pairs mating head to head. Any orbital cannot be occupied with more than 2 electrons, so the maximum number of electrons taken by one orbital is 2 electrons. Each of them rotate around its own axis while revolving around the nucleus. The same idea for the motion of planets around the sun. Each planet rotates around its axis, and at the same time they are rotating around the sun. The same idea here, the electron rotates around its axis and rotates at the same time around the nucleus. Each orbital, as we mentioned, filled with 2 electrons. So S sublevel consists of one orbital, so it is filled with 2 electrons. P sublevel composed of 3 orbitals, so it is filled with 6 electrons. D sublevel consists of 5 orbitals, so it is filled with 10 electrons. F sublevel has 7 orbitals, so it is filled with 14 electrons. Let's take an example. What are the probable values of magnetic quantum number when subsidiary quantum number equals 3? The answer is, the probable magnetic quantum number ranges between negative L to positive L. So we have here the probable values from negative 3 till positive 3. We have here the number of orbitals are 7. The last quantum number is spin quantum number, which is denoted by ms. This quantum number describes the spin motion or the rotation of electrons around the nucleus. As we mentioned in magnetic quantum number, any orbital cannot be occupied by more than 2 electrons. Each electron spins on its own axis during its orbiting around the nucleus. So the electron has 2 rotations, one around its axis and the other one around the nucleus. You can observe here that we have 2 electrons rotating in opposite direction. As a result of this rotation, a magnetic field arises, but the magnetic field in the first electron is opposite to the magnetic field of the other electron. So, as a result of this, the repulsion force between the 2 electrons decreases. The spin quantum number defines the type of motion or spinning of electron around its axis in the orbital. We have 2 types of spinning. Number 1, an electron moves clockwise or with the direction of the clock, and it takes the spin quantum number for this electron will be positive half. The second, anti-clockwise or in the opposite direction of the clock, and its spin quantum number will be negative half. After finishing the 4 quantum numbers, we have here a summary for what we have said in this lesson. The number of energy sublevels equal to the number of principal level to which they belong. It means that if we are in energy level number 3, so we have 3 sublevels. Number 2, the number of orbitals within a principal energy level equal square the number of level. So if we are in the second energy level, 2 to the power 2, so we have in this energy level 4 orbitals. The number of electrons occupying a given principal energy level equal 2 times the square of this level, or you can apply the rule 2n to the power 2 to know how many electrons can occupy this energy level. For example, the second energy level can be occupied by 8 electrons. Why they are 8? 2 times 2 to the power 2, they will be 8 electrons. Each sublevel consists of orbitals which are equal to L plus 1. So, for example, if we have here D sublevel, its subsidiary quantum number is 2. I want to know the number of orbitals in D sublevels. 2 times 2 plus 1, it will be 5 orbitals. And this table contain all the relations or all the quantum number values we mentioned in the previous slides. Thanks for listening.